Is my screen share looking good?
Yes.
Cool. So I'm going to get started in about a minute. I've got about 45 minutes of talk, and then we might have people might have some things they want to discuss, because there's some things I cover in detail and some things I don't. So I'm not really sure what people needed to hear. So I'm going to go ahead and mute my camera to save bandwidth. All right, well, if anybody wants to come later, they'll just miss my opening remarks here. So this is managing X.509 certificates in your environment. I put this together because a lot of organizations are adding TLS to their infrastructure, and there's a lot of confusion about the roles of X.509 certificates and how to effectively employ them in your architecture. I work in a pretty high security environment, and I cannot tell you how many people really have no idea how the certificates work in the whole environment. So I'm going to start really basic and just talk about encryption, because when most people think about adding TLS to their environment, they're thinking about encrypting data in transit, which is an important control. Most cryptography, in fact, the bulk cryptography used by these encrypted tunnels, even SSH, whatever, is that you use a symmetric encryption algorithm. In that case, the key is the same on either side, and the problem with just relying on symmetric keys is that you have to have a pre-existing relationship between the two endpoints in order to exchange the key. So what everything else, what the real basis for modern secure tunnels is asymmetric cryptography. In asymmetric cryptography, you have a key pair. You designate one of the keys to be a private key, and you keep that secret. And then the other you designate as the public key, and you can send that to anyone. So the thing with asymmetric encryption is that you need both keys to go from plain text to ciphertext and back to plain text. So this way, if you have a key pair, you can send the public key to an unknown party, and this allows secure communication between the two endpoints, even if they have no prior relationship. At the very least, someone with the public key can encrypt a bulk encryption key and send it to you, so that now you have the same key, even though you didn't have to establish a prior relationship. So you don't need the X.509 certificate for this key exchange. In fact, Secure Shell sets up a secure connection using an ephemeral key pair just created for the session. And in fact, since version 1.1, TLS also sets up that encrypted connection with an ephemeral key pair. So what is the X.509 certificate even for? And what it's for is authentication. So an X.509 certificate attaches an identity to a key pair. And that's its job, is to attach an identity to a key pair. And originally this was intended to identify users, but it ended up being used most often to identify servers. There are still client certificates, of course, and we'll call both client certificates entity certificates. All other certificates are CA certificates that exist to sign entity certificates. Okay, so most of the time that we want to communicate securely with a server, at least in our daily lives, we're conducting e-commerce. So in this case, and this is how, of course, TLS and SSL, starting with SSL, became a big deal with HTTPS. And in this case, it's really important to be confident that we're talking to the correct server. Obviously, we want our data to be secure, but we also need to know for certain who we're talking to. So when we're managing a private network, like our development systems, our pipelines, and the parts of the deployment that are inside the firewall, a lot of people just use unencrypted connections, or they use TLS, but they tend to think of it in terms of encrypting their traffic. So they do the minimum possible to set up TLS, so they do as little as possible to enable it. And this usually means using self-signed certificates, or using the same certificate for every internal endpoint, or sometimes tools come with their own default certificates. And this removes the endpoint authentication feature of TLS. But it's one of its biggest features. And there's an emerging best practice that you may already know that's making endpoint authentication mandatory. And that's Zero Trust Architecture, or ZTA. To sum up what ZTA is, if you're unfamiliar, it is trust nothing, verify everything. So TLS so trust nothing means that you can't trust your network to be secure. So obviously that's the encryption part, but you also can't trust that the server on the other side end of your connection is a legitimate server that you're supposed to send your encrypted data to. So TLS solves both of these problems by keeping your network traffic secret, but also by forcing your server endpoints to identify themselves. This means that if you need to deploy your microservices and CI/CD tools with TLS enabled. It also means that configuring these endpoints with proper X.509 certificates to identify them. And a lot of people know how to install X.509 certificates, but how to manage them in an enterprise is not something that they've had to do. So I'm going to talk about understanding what X.509 certificates are and how to manage them effectively. So rolling out TLS with private certificates. A lot of these people these days don't even, a lot of tools these days don't let you install without TLS. They come with default certificates in case you don't have any, so they can come up, or maybe you create a few certificates and put them in your servers. Then you get your first developer complaint. I can't connect to GitLab anymore, and they show you this error. And here it says certificate signed by unknown authority. So this is when people start looking up all of the ignore TLS certificate error features of the tools they're using. So this is where you get the -Ks in your curl statements cropping up, and when people invoke, pip with trusted host, and all the other tools will have, almost every tool will have a ignore TLS error switch or configuration, so that you can just move on with your lives, even though you can't verify these certificates. So what you've done is you've deployed TLS, and you have certificates on that TLS because you can't have TLS without a server certificate. But you're violating zero trust architecture because your clients always trust and never verify. So let's look at all the things you have to do to fix this. And we'll start with understanding certificate validation basics. So the first problem is that your internally generated certificates are not going to be signed by a well-known CA. This is what the error in the previous slide was complaining about. The reason why the client trusts a server certificate is that it's signed by a trusted CA. So a lot of times people create self-signed certificates for an entity, and this may be rejected by TLS verification because entities should not have self-signed certificates. Because if an entity's certificate is self-signed, it can't be verified. So it depends on how picky your TLS stack is being, but that may be just rejected out of hand. So if the self-signed certificate is marked as a CA certificate, that's normal because CA root certificates are self-signed certificates. But then it shouldn't be used as an entity certificate. If you try to add your self-signed certificate to a trust store and it's not flagged as a CA certificate, it might not be recognized as a trust anchor. So TLDR, don't do that. You hear people say, oh, self-signed certificates, those are bad. Well, all CA root certificates are self-signed, but they should stay as CA root certificates. And the certificates that you distribute should not be self-signed certificates. I think most people know that they should create a CA signing certificate and use that to generate their entity certificates. And if we trust a certificate because it's signed by a particular CA, then how do we know to trust that CA? And the answer is we just do. And the longer answer is that the CA certificate has to be preloaded into a trust store on the client. So that's your browser comes with hundreds of pre-trusted CAs, including like Let's Encrypt these days. I was talking to Jeff before the meeting about the headaches of deploying certificates with Java, and so you have to put stuff in that truststore.jks in order for it to be trusted to be trusted. So and that needs to exist on the client before you make the connection. So this is why we sometimes refer to CA root certificates as trust anchors, because that they go onto the client and they're pre-trusted. And this is not like symmetric encryption, because you can give the public portion of your root certificate to anyone who wants it. And then they can use that as a trust anchor if they want to trust that CA. So this means that if you have a private root, but the bottom line is that if you have a private root certificate, you're going to need to add it to the trust stores on all of your clients so that it can act as that trust anchor. So on Windows, we're talking about this too. On Windows, there's a standard place to put your CA root certificates. On Linux, there could be multiple places. For example, if you want the CLI to, the Docker CLI to trust the CA of your private image registry, you need to put the CA certificate here. Other places would be here or here. And there may, and this is just on Ubuntu. There may be there are other places on Red Hat where you need to put the certificates. Now, one thing you can do is have a bundle of certificates and just link across all these different places, but you do need to find them. So chances are that after an initial round of deploying your root certificates everywhere that you can think of, you'll be finding more places. So it's really important that you put your CA certificate where people can easily find it, because if they spin up a new workstation or a new cluster, or they find a new place to put their where the CA certificate has to go, maybe a Java key store, they need to be able to get it easily, and preferably from within your build pipelines. So some people seem to think that the CA certificate is some kind of carefully guarded secret, but that's the exact opposite of the case. The private key associated with your CA certificates should be a closely guarded secret, but the public portion is again public, so you can give it out. And the only reason why you wouldn't give your private CA root certificate to somebody outside your organization is it might give them a little bit of information about your internal network, but it's not harmful if they got a hold of it. So I've kind of jumped around a bit here, so let's get back to looking at what the CA stack is going to review to verify an entity certificate. So the first step that is obviously the signature, so you're going to have an issuer on your server certificate, and that needs to match the common name attribute of the signing certificate. And that's how the names are connected. And so that's going to be checked. Once it's looking at the root certificate, so it's going to find the root certificate for that name that issued your server certificate, and then it's going to use the public key inside the CA certificate to validate the signature on your server certificate. So that's what most people understand, and that's why you need that CA certificate out there. The next part is name. It used to be that the server name had to be in the common name attribute of the certificate, but there were some issues with that. So if you have a GitLab.internal, that's the host name of your GitLab. If you have a GitLab.internal, it should have a certificate with the name GitLab.internal. And this used to be in the common name, but we'll talk a little bit more about that in a sec. I just wanted to say that you can wildcard the DNS names. I think everybody knows this, but do not wildcard your entire domain. And you see that's one of the shortcuts people take, is they'll create a server certificate with their entire domain wildcarded, and they'll just pass it out to every single machine. And that again defeats the TLS endpoint authentication component and subverts the zero trust architecture. So if you have all these internal services like GitLab, SonarQube, Artifactory that you've deployed, create a separate server certificate for each one. So getting back, so the original idea was that you could just match against the common name of the certificate, and there are some issues with that I don't want to get into, but there's another attribute that was introduced later called the subject alternate name, and that's where you look for a server certificate. That's where you look for a name match, and the common name is only used if you don't find a name match in the subject alternate name. So and so that would look like this, where you have a subject. The subject is cn equals star.google.com. Now, the biggest advantage of the SAN is that each type of entry in the subject alternate name has a type. Each entry has a type. So if you're giving a DNS name to match, it's the type of that field that entry is DNS name, and you also have IP address entry. So a DNS entry must be a proper DNS name. That's not true of the common name, which was the problem. And the IP address entry must be a proper IPv4 or IPv6 fixed IP address. So this allows for a certificate to be used for a bunch of different servers. Again, for an internally used certificate, specificity is more secure. So for external certificates, you're just trying to get the browser to be happy with whatever you're sending it. So you see that this Google certificate matches quite a few different domain names, and this, you can only see part of the list here. Now note that at the top of the list it says not critical. So this means that there is a valid CN common name attribute that can be used. As you can see, it says start@google.com. So it's telling the TLS stack, it's not critical to do a name match against here. It's going to start looking there, but if it doesn't find, and you'll see start.google.com is at the top of the list. So anything that matches the common name would match there. But it's just telling the TLS thing that I've got a good one in the common name if you run out of options, and the subject alternate name, the SAN. So for your internal certificates, omit the common name and mark your SAN critical. This is because, again, you're wanting to give the TLS stacks that are verifying this fewer options. You want it to be as specific as possible. So put the most specific DNS name you can into the SAN and the IP address, because that allows people to attach to contact the server just using the IP address and still do a full validation. I don't know if you've ever gone to a TLS endpoint with an IP address and then it says, I don't recognize this, because it's looking for a server name. And that name comes from the host portion of the URL. So that's the name that it wants to match on. So if you have IP address in your URL, you're going to want an IP address in your subject alternate name. For client certificates, which aren't widely used, but the subject name is usually important because it's usually talking about a person, or it's frequently talking about a person. We're seeing more and more machine-to-machine use of client certificates, but if it's talking about a person, subject, distinguished name is where we want to put it. Also, but subject alternate name has some features like email address that you might want to use as a match, and you can look that up. Chances are it's not being used in your org. So that's it. The not critical. You'll see that in commercial certs. You don't want to do that on your private certs. So just quickly, I think everyone knows this. Validation is also going to check validity dates. There's a not before date and a not after date. Now here they're called issued on and expired on. And the reason that the not before date is sometimes called issued on is because you're not really supposed to set it to a value in the future. So it kind of defaults to the date at which you created the certificate. So the issued on date and the not before date are usually the same. So, and then obviously the last date at which you can use this certificate legitimately is the not after date, and so you can also call that expires on. So that's just what this UI is calling it, but officially it's the not before and not after date. There is a set of flags called key usage, and this is from the original X.509 specification. And there's a bunch of them, but here's the ones that you're going to want to understand. Digital signature, that's for verifying digital signatures, basically TLS. So your CA certificate's going to want to be able to verify digital signatures because it's checking signatures on other certificates. Also for document signing, also for code signing, if you're using code signing. I think it's also used if you want to digitally sign emails, but generally digital signature is kind of pretty much applies to most certificates usage. Key cert sign, that means that the key in the certificate is used to sign other keys, basically for creating certificates. So that your CA certificates must have key cert signs set, and your entity certificates must not have key cert signs set. If you have a mismatch between whether something's a CA cert and something's an entity cert via key cert sign, it may be rejected. CRL sign allows signing of certificate revocation lists, and that has a lot to do with the tool you choose and how it manages certificate revocation lists. So there is extended key usage. This was added later when the use cases for X.509 certificates started to really flesh out. And so you've got server auth. So all of your server certificates should have this set. Client auth, that's for your client side certificates, whether they're machine certificates or personal. Code signing, so that is an additional one that should be turned on if you're specifically using a certificate for signing code. Email protection is specifically for SMIME email signing and encryption. And then OCSP signing. OCSP is the new protocol for is a more efficient way of getting revocation lists or revocation information. Since it was added later, there is now a separate usage flag for signing OCSP responses. And the reason why the CRLs and OCSP responses are signed is that they're frequently, as if they're usually offered over unencrypted plain text HTTP connections. And the reason for that is that since they're at the very, when you're checking revocation of certificates, you're not really sure what certificates to trust and what certificates not to trust. So they will give you the list of revoked certificates or validate a certificate revocation with OCSP over plain text, but they sign the responses. That's usually in the root certificates. Okay. Although you may have an intermediate CA certificate that's responsible for signing those. All right. So now we're talking about CAs, and we're closing in on running your own CA to generate internal certificates. So the fact is you can create all the certificates that you will need using OpenSSL on the command line. And maybe it's worth learning how to do that just to get a real hands-on feel. But there's more to managing your certificates, so you're not going to want to do that. You should really use a tool that has some certificate management capabilities. If you have 2 servers, you can probably manage them ad hoc. Just use OpenSSL on the command line. But as your PKI grows, you'll get swamped, and you don't want to have to retool during that period of growth. So run your CA like you have 10 times the scope. So if you have 2 servers, run your CA like you have 20. And a management tool is also going to give you other capabilities beyond creating certificates, like, for example, managing your certificate revocation list. So you'll need to track the certificates you've issued, and then you'll need to be able to have those certificate revocation lists or operate an OCSP endpoint. And that's another thing that your tool is going to do for you. Because without these, you won't be able to effectively revoke certificates, which is part of your PKI security. And advanced tools may also support the Automatic Certificate Management Environment, or ACME standards. That's what Let's Encrypt uses to issue certificates. And you can use it to automate the issuance of any kind of certificate. If you're going to get into automating your PKI, make sure that you've managed that you've mastered the basics. If you haven't, mastered the basics of certificate management, do not automate your certificate management, because you'll probably shoot yourself in the foot. All right, so we're going to start our own CA. Obviously, the first thing we need to do is create a root certificate. This is going to be the certificate you're going to need copied everywhere. I was just dealing with somebody who had a user certificate signed. He's from the FAA, and so I was trying to track down what root certificate. It turns out that every certificate issued by the General Services Administration, the GSA, uses the same root. So all civilian agencies have the same root certificate, which is pretty crazy. But you can imagine what a big deal it is when that certificate changes. So that certificate has a very long life. I think it lasts 10 years. And you can use the certificate to sign your entity certificates, which might seem like a good thing to do if you've got a small PKI. You don't want to get too fancy. But even in a small PKI, there's a reason why you want to create an intermediate signing certificate. So do you go with direct sign certificates, or do you go with intermediate signing certificates. Now, some very large organizations will use intermediate signing certificates to break down the work. For example, in the GSA, there's like 20 different government agencies, so each one of those has an intermediate signing certificate. And then they've got different divisions, and their certificate trust chain is humongous. And that's just so that they can manage all the different places where they need to issue certificates. For a small PKI, that's not why you want an intermediate certificate. So let's look at this. Excuse me. So everyone understands that the server has to send its TLS certificate down to the client so it can validate it. What a lot of people don't know is what happens with intermediate certificates. Those need to be sent by the server as well. So all of the certificates that you see in the green ring, the green oval, those are all sent down from the server on a TLS handshake. And the root certificate is not sent because that needs to already be on the client. And if you don't send, if you just put your server certificate onto your server and you don't include the intermediate certificates, then your validation's not going to work. I've seen that confuse a lot of people, where they have an intermediate cert and they don't put it on their server and none of their validations work. And that's why. It's because they didn't include the intermediate certificates in their bundle. So let's talk about intermediate certificates and why you want to go to that effort. It's actually pretty easy to implement, especially on Linux. So you take the PEM file for your intermediate cert and the PEM file for your server cert, and you just concatenate them into one file. So here I've got server.pem, intermediate.pem, cat them together into full chain.pem, and I put that as my, when you're configuring your server to point to the server certificate, you point it at that bundle. Now, you only need the private key for your server certificate, but you need the full chain to meet your obligation to send the intermediate certificates as well. So because the intermediate certificates need to be distributed with the server certificates that they sign, it creates an additional server and certificate management overhead. So for this reason, a lot of people would want to avoid using intermediate certificates. But a good reason to have an intermediate certificate is to protect your root certificate. In fact, if you use the small step CA certificate management tool, it actually forces you to do this. So after you create an intermediate certificate, you take the private key of your root certificate offline where it can't be stolen by a network intruder. And this is a great practice, but having an online root certificate that signs everything might be secure enough for your needs. But this allows you to have a really long-lived root certificate and know that it's safe, because you only take the private key online when you need to create an intermediate cert, which will hopefully be much less frequent. So, because then that intermediate cert should sign a bunch of server certs. So, but finally, so that really is kind of the key to making a 10-year root certificate, because you can be pretty confident that over those 10 years, there's going to be very little opportunity to steal the private key for your root certificate. All right. So take your root certificate private key offline. All right, so now I'm going to talk about basic constraints. There's another little known field inside the X.509 certificate. It's got two fields. One is CA and the other one's path-len constraint. Now I also have key usage here just to remind you that on your CA certificates, the cert sign needs to be flagged true. So CA is set to true for CA certificates and false for entity certificates. Path-len constraint tells you how deep the trust chain is allowed to go underneath that CA certificate. If you don't set path-len constraint, you have no path length constraint, and your CA trust chain can go as deep as you want. Don't do that, because that introduces the risk of rogue CA chains. So what you want to do is you want to set your intermediate certs, or the certs that are right above your entity certs. You want to set the path-len constraint to 0, meaning you cannot mint any more CAs underneath this. And then the one above that would be path-len constraint 1. And I doubt you're ever going to want more than 1 deep like this. But if you do, obviously just kind of follow the pattern there. And then, your entities should all have CA set to false. Path-len constraint is not applicable, and they should not obviously be set to key cert sign. So let's talk about the certificate management tools. Now that we've gone over all the validation that a certificate goes through and how to create the certificate trust chain, we're going to talk about using certificate management tools. And I'm not going to get very deep into this. And the reason I'm not going to get very deep into this is I wanted to cover basically the policy and procedure level of this. I don't know what your organization needs and what its budget is, because obviously you've got some money. There's some great tools. If you don't have money, the tools I would recommend looking at are CFFSL, which is from Cloudflare, and it's mostly a bunch of scripts. It's a little bit technical, not super user friendly, but it is fully open source. The other one that looks really good, I haven't used it, is Small Step CA. This is one of those ones that has a free tier and an enterprise tier. For example, the enterprise tier supports the Acme protocol if you want to get really fancy, but the free tier will do pretty much everything you need. My organization is actually using the CA that's built into Microsoft Active Directory, and nothing wrong with that. But Small Step, I think, is a better tool. I wasn't around when we made that decision, but those are the ones I would recommend looking at if you don't have a certificate management tool and you don't have a budget. But don't run out and install them quite yet, because we have a few more things to talk about. And one of them is certificate expiration dates. So when a certificate expires, it has to be replaced, not renewed. Don't reuse key pairs, replace it. So once the CA generates the replacement certificate, it needs to be deployed in place of the expiring certificate. So you need to make that deployment part of your infrastructure as code, your configuration as code, or your build pipelines, or whatever you need to do to simplify it. If you can just drop that new replacement certificate into an S3 bucket or a Git repo or Artifactory and have it installed by automation, that's what you want to do, because you don't want to have to go around creating certificate bundles and installing them by hand. And having intermediate signing certificates can basically double the management burden, because obviously you have to install a new server certificate when that's expiring, but you also have to, since the server also has to have a copy of its intermediate CA certificate, you need to replace it when that expires. So you end up with these dates. So here you see I have to do a replacement when the CA certificate expires, and then one where and then when the server certificate expires. So this is a lot of renewal events, and you could try to synchronize your CA renewals and your server renewals, but that's really a fool's errand, because servers come and go, and really the creation of server certificates is always just going to end up being asynchronous to the creation of certificate authority certificates. So I have a recommendation. So here we have years, year 0, 1, 2, 3, 4, 5, 6. And the first certificate you need to create is your root certificate. And I'm going to say 10 years. So it's going off the right-hand edge there. And so next, we'll create an intermediate signing certificate. So again, we can take once we've created that, we can take the root private key offline. And we'll give that a 2-year lifespan. And we'll call this one certificate A, because we're going to have to replace it with certificate B. And here's the trick. So we'll create intermediate certificate B starting a year later, and we'll give it a 2-year, and then we'll do the same with C. So the creation of the intermediate certificates will be staggered by 1 year, and they'll all have a 2-year expiration. Now what happens is we bring up the server and we give it a 1-year expiration, and then at the end of that year, we replace it, but we replace it with a new certificate signed by certificate B, and then the end of that year, certificate C. So what happens is that a server certificate an intermediate certificate never expires during the time when the server certificates it signed also expire or have expired. So you notice that the expiration of intermediate CA, A's, B, and C is always later, after we've already replaced the server certificate. So what that does is now you'll see that my renewal events happen at the end of the server certificate expiring and aren't driven at all by when the intermediate CAs expire. So you don't have to do the 1-year lifespan or the 1-year regimentation here. You can make it longer, make it shorter. Just if you keep that 2-to-1 expiration between intermediate CA and server CAs, then you'll preserve the minimizing of the renewal events. And you can also make it super short. And returning to this Google certificate we looked at earlier, I don't know if you noticed this, but this certificate is only valid for 12 weeks. But this is a highly visible certificate that is on the public internet. So there's a lot of risk associated with it, because everybody would love to be able to crack this certificate and steal the private key or crack the private key, whatever. There are probably nation states that would try to do this. So they have a super short lifespan on this certificate. Your risk factors are going to be much, much lower for an internal PKI, and just kind of evaluate them. Say, how much risk are we willing to take? And so you might, take that 1-year cadence that I had and turn it into 2 years. It's really up to you. All right. So who's ready to issue some certificates? Let's review where we are. We picked out and set up our certificate management software. Oh, a typo there. We have a plan to distribute certificates where they need to go with automation or whatever. And that includes infrastructure as code, configuration as code, and deployment pipelines, whatever we can do to make that as easy as possible. And we have a policy for certificate expiration. Because when people are creating certificates, they always want to know, well, how long should I make this last? Now we have a policy, so we're good. So we're ready to start issuing certificates, right? No, not yet. We have to talk about PKI. So a certificate authority and a certificate authority management software is not a PKI. It's the enablement of the PKI. So let's talk about what a full public key infrastructure is, especially on a micro scale, because PKIs are a deep subject, but you don't want to go that deep for your internal CA. So you can keep it pretty simple. So this is a diagram of a basic PKI, and it starts with a user who needs, or an administrator, sysadmin who needs a certificate for their server. So they create a certificate signing request, and a certificate signing request basically contains identity information and a public key. And remember, an X.509 certificate connects an identity to a key pair. So that's what we need to send to get our certificate back, is that identity and the public portion of that key pair. So we send that off to the registration authority, or the RA. Now, don't worry about how that transmission works. It could be an email, it could be an S3 bucket, could be on a thumb drive. It really doesn't matter, because the submission mechanism doesn't have to be secure, because the RA will perform vetting on the submission. The RA is a function, so the registration authority is not, there will be some support in your tool for receiving certificate signing requests, but the registration authority itself is actually an office function that's conducted by a person or people. So the RA needs to be able to verify that the request is legitimate. It did come from someone in your organization. Is the identity information valid? Does it meet the requirements? Like, did they wildcard your entire domain, or did they wildcard a subdomain that's just too broad? That kind of stuff. Did they include IP addresses for their server, if that's appropriate? Does the person requesting the certificate have any business requesting this certificate, or is this for a server they don't even manage? So that's what the RA needs to determine. And if you have a small organization, this might be really easy, because the RA might be sitting next to the person who requested it, or they just know them personally. But but whether or not it's an easy job, it's a very important job, and it can't be done by the same person who performs the CA function. So this is a separation of duties issue, and it's really critical in reducing fraud, errors, perfectly well-meaning errors can happen, misuse of information, and any insider threats that might be cropping up in your organization. So, and in some circumstances, this might even be a regulatory requirement if you're governed by Sarbanes-Oxley, but you should know that. More practically, the RA is a QA quality check mechanism to keep garbage requests from going to the CA and making them boot it. But if a request goes to the CA, it should be fully vetted. So the CA doesn't have to waste any of their time vetting it. And, once your organization starts to get, even medium size, you may start to have people who are a little unclear on the concept and send you some garbage requests. So the RA basically bounces those requests and makes sure that the CA gets requests that are ready to sign. But even if you have a tiny organization, find two different people to do RA and CA. So let's talk about CA. So the certificate, the CA, the certificate authority, receives approved CSRs from the RA, and then they sign it with the appropriate CA certificate. And the signed certificate, and I guess probably the intermediate, if they'll need that, are delivered to the original requester. This delivery, again, does not need to be super secure, because you're not sending the private key is the big secret thing that has to be well protected, and the requester does not send this with a certificate signing request. So, your tool will probably provide a place to download the certificates. Microsoft Active Directory does not handle this real well, but if you've got a simple tool that doesn't really distribute the certificates that well, email them, whatever, put them in a bucket, doesn't not matter. Just that goes from the CA to the administrator who asked for it, and then they go and they install it on their server. And that's the life cycle. And there's one more desk on this, and that's the verification authority or validation authority, or sometimes called the verification authority. This is where systems can go to check that an otherwise valid certificate, it's got all the right things, has not been revoked. So if the CA revokes a certificate, it tells the validation authority. This is actually fully automated by your tool, or should be fully automated by your tool. So your tool should provide an OCSP endpoint to answer queries about certificate validity, or a place to download a CRL of revoked certificates. So a CRL is just a big long list of certificates, and if you've revoked a lot of certificates, it can get very, very big. Obviously, you don't need to include certificates that have since expired, but because of the unwieldiness of CRL, OCSP was created to be a little bit more efficient. So you should provide both, because sometimes a lot of modern tools will check OCSP, but some of them won't. Some of them demand a CRL. So you need to provide both, and that should be handled by your tool. Now, one thing to point out here is that the endpoints that provide your CRL and your OCSP protocol need to be as visible as possible. Obviously, the CA functionality and your keys and all that need to be very well protected, but the validation authority endpoints need to be very accessible, at least they need to be visible to any client that might need to check the validity of one of the certificates that you issued. So we're talking about, I talked about passing around these certificates. Let's talk about file formats for a bit, because this is also a big source of confusion. You've probably seen several extensions, seen PEM, DIR, SIR, and CERT. So first of all, there are only two file formats for X.509 certificates. And that's DIR and PEM. The SIR and CERT extensions don't necessarily mean anything. They can sometimes they hold a DIR format, sometimes they hold a PEM format. There's no standard. We're just stuck with them for legacy reasons. The key thing is that if you see a file that says .sir or .cert, it only contains the certificate. Even if it's in a format that can contain the key, it won't. Or at least it shouldn't, I should say. So that's one particularly useful thing about those extensions. However, so let's talk about PEM and DIR, because those are the real file formats. So the X.509 format is defined by the Abstract Syntax Notation 1, ASN 1. It's a really old way of describing structured, tagged data formats. It, as the name implies, it's completely abstract. There's no official or no a priori digital format that goes with ASN1. So you can take an ASN1 structure and you could write it out as XML, or you could write it out as JSON. So, and the reason why X.509 certificates are never written out as XML or JSON is because they were invented a decade before either one of those existed. So we got stuck with digital, with the distinguish encoding rules, DIR. And the distinguish encoding rules are a binary format that that can take an ASN1 description and render it as a binary file. Okay, so if you can't cat the file out, if you try to cat the file and it says this is a binary file, it's dir. If it spits out text, it's PEM. So what is PEM? PEM stands for Privacy Enhanced Mail. You don't need to remember that. It's not going to be on the test. But the reason it's called Privacy Enhanced Mail is that this was an early 1990s project aimed at improving email security. This is before SMIME. And part of the system required that you be able to email your certificate images to the other people so that they could use them to check your digital signatures and so forth. Now, SMTP does not handle binary at all, really, and it still doesn't. So, you know, if you've ever cracked open the source code of your emails, it's full of what? Base 64. So basically, a dir file, a PEM file is base 64 encoded dir file. So you take the dir file, you base 64 encode it, and then you sandwich it between these two delimiters, and that's PEM file format. Ta-da! So again, if you dump it out and you see begin certificate, end certificate, that is PEM file. Now the cool thing about PEM is that since it's just a base 64 block of data delimited by these delimiters, you can actually see if this is the next. Yeah. Oops. Yeah, you can actually put multiple items into a single file because you'll have the delimiters, the base 64, and then you can have another delimiter in base 64. So PEM can contain the private key and the certificate. And it's actually got different delimiters for RSA private key versus, I forget what the other one is, but the old, I think it was Diffie-Hellman. Anyway, so if you get a dir file, that's the digital encoding of the X.509 certificate, and it will not contain the private key because it's only describing what's in the spec for the certificate, and the private key is not part of the certificate, so it won't have the private key. A PEM file can include the private key, and it can be encrypted using the public key cryptography standard number 8. It's PKSC number 8. And then on the bottom line here, I have PKSC number 12. That is another file format that can contain certificate. It can contain the private key or one or the other. It can also contain additional metadata, like, for example, like a friendly name for the certificate. And it's used for transferring certificates around with all the data that you might need. And it's not usually used directly for configuring things. Usually you have to convert it or transmute it into the format that you need. And the file extensions for that are P12 and PFX. So if you see those, that's what those are. You probably won't be able to install those directly into the place you need to install them, so you'll have to convert them to a PEM or dir. And frequently, PEM, I think, is probably the most common format because it's just so easy to deal with. And so I was talking earlier about certificate bundles, and you saw how I just concatenated 2 PEM files to make a certificate bundle. On Linux, you'll find these certificate bundles that are full of root CAs, and it's just PEM, all these concatenated PEM format certificates. All right. So one more thing about PEM that's cool is that since it's all ASCII, you can print it out. So if you want to take your private key, especially your root CA private key offline, you can print it and stick it somewhere safe. You could also copy it to a thumb drive. Maybe you have a floppy drive lying around or DVD writer. But all of those are prone to degradation, whereas if you print it on a piece of paper, it will probably be fully readable next time you need it. So unless there's a fire, but thumb drives don't survive fires very well either. So that's just another cool thing about PEM that you might consider if you need to take your private key and put it somewhere safe. So one more thing before you start your CA for your internal organization. We've covered pretty much everything, but there's still something you need to create a PKI. Now, an enterprise class PKI should have a document called a certification policy and another document called a certification practice statements. You probably don't need that for a small PKI. And one of the reasons why you don't need those are they're essentially legal documents that talk about your roles and responsibilities. And these are critical if you are a commercial certificate authority. So they become part of your contracts and your service level agreements. And since you're not cutting CAs for paying customers, cutting certificates for paying customers, you generally can ignore those. But what you will need is basically, you will need to write down some stuff. So like I talked about how the RA has rules around, you get a certificate and before you send it to the CA, you have to do all these vettings. Now, the people in your organization requesting the certificate need to know those rules. And they also need to know who the RA is and how to send this certificate signing request to the RA. And they might need to have instructions on how to generate a CSR, certificate signing request, to get all the right things in it. And they also need to be told how to, and you can't help them with that, by the way. A CSR is signed, so if they don't generate it right, you have to send it back and have them regenerate. So you want them to know ahead of time how to do it right. And things like how to specify the subject alternate names and what should those subject alternate names be. Like for client certificates, you need to ensure that the subject name is correct. Is it like family name, comma, first name or given name, or is it just the name written out? Is there some kind of ID number tacked on the end of it? A lot of people do that. Do you need the email address in the subject as a subject alternate name? And is this mandatory or optional? You need all those rules. The people requesting need to be given as clear instructions as possible on how to create those signing requests and how to submit their signing requests and what to expect after those signing requests are submitted. Like, how will they know if it was accepted or rejected, that kind of stuff. So you need to decide all that stuff before you start generating certificates, and you need to write it down, and you need to make it available to the PKI team so they know how everything's supposed to work, and anybody in your organization who needs to obtain a certificate. So basically you need to generate an informative pamphlet called "So You Want a Certificate," and make that available on Confluence or however you distribute information in your organization. And now that you have a document describing your policies and procedures, and there's no confusion about how and why certificates need to be generated, you can go ahead and start issuing certificates. And I'm going to put up as my last slide just a little reference of the do's and don'ts that we've covered in this talk. And oh, I see there's this got cut off, but it's supposed to say the last one on the under don't is let the RA and CA functions be different people. I don't know how that got screwed up. Anyway, any questions on any of this? Yes, Bon Lee.
Firstly, thanks very much for this walkthrough, Charles. As this is very new to me, and I can't say I understand everything that you have presented. So I wonder if there is any, tutorial or 101 with an environment that I could play around with and perhaps put to practice some of the things you presented to us?
I don't know of one offhand, but what I would recommend is go to YouTube and search for, like, if you want a product, like if you want to see how people say use small step CA, and you want to watch them kind of go through the process of using that, search for small step tutorial, or step CA is also another name for it, tutorial. If you need to understand the basics of see, I'm not quite sure. Can you be more specific about stuff that you'd like to know more about?
So, for example, I like to do an exercise of the firstly the different parts of the PKI, and secondly to try to generate some certificates, public and private certificates, and then exchange it between two servers, just to reinforce some of the things I've learned in this presentation. That would be the objective.
Okay, what thing I would recommend, just to really get a very firm grounding, is to and you can actually ask like ChatGPT to give you instructions on doing this, but look up, set up like Nginx or Apache or some other easy to set up web server, or it could be like like a Python web server, whatever server you like. I tend to like Apache Tomcat, but set that server up. Actually, Tomcat's bad because you'll have to create Java key stores. Yeah, stick with Apache or Nginx, and use OpenSSL on the command line to generate some certificates. And there are instructions. You should find plenty of tutorials, both in video format or in articles, on how to create a couple of certificates, a root certificate and a server certificate using OpenSSL on the command line, and then how to take those files and put them into Nginx in such a way that you can browse that, and that should give you a really firm understanding of what files get generated and how they need to be put. And then you're going to want to point your browser to your new web endpoint, and you're going to want to access it. And then you're probably going to get an error that says like, oh, this is not secure. So you're going to need to figure out, okay, well, I generated my root certificate and I signed a server certificate and I put it in Nginx, and now when I connect to Nginx, I'm getting a problem. So the first thing you need to do is figure out how to take that root certificate, the public part, and put it into your browser. Like with Mozilla, it's pretty easy. You actually do it inside the browser. But if you're not using Mozilla, if you're using Chrome on Linux, it's really hard. If you're using Windows, it's really easy to take that root certificate and put it into the place where you can say where the browser will now trust it. So now your browser will trust the certificate coming from Nginx, but you'll still probably get an error if you're using the IP address. So you want to go into your hosts file, wherever that is on your operating system, and set up like a test server.internal or test server as the name, and you want to make that the same name you put in the certificate. So now when you browse, you go to like test server :8080, and it goes and it sets up the secure connection. It gets the server certificate and says, oh, okay, I trust this because you put the root certificate you created into the trust store. So I know I can trust the certificate. And then it looks at the name and it says, okay, we went to test server. Is test server the name that's inside the certificate that I got from the server? And it goes, oh, it is. And now you have a secure connection and it works, and you don't get any errors from the browser. Does that make sense?
Yes, yes. Thanks for that. Thanks for that advice. I think I'll give it a shot. Thanks. Much appreciated.
Yeah, thank you.
Mm.
So everybody else was like that was like total review for you guys.
Thank you.
Jeff, did that fill in any blanks for you, or was this all stuff you knew?
I thought it was a nice overview. There's parts that were left out, but that's kind of two sides of the same coin. And if you're talking about one side, you kind of don't tend to talk about the other side.
Yeah. I'm never quite sure how much information to put into one of these things, because especially when I'm talking about TLS and X.509 certificates, because I've seen, some very technically experienced people get completely confused by very basic things. So I try to start with very basic, but is there some stuff that you think I should, I like Bon Lee's suggestion of talking about how to do a little experiment on your own. Is there some stuff that you would put in as well?
Well, you can actually use OpenSSL as a client, as a TLS client. So you don't actually need a browser to test your connection to your TLS service, whatever that is.
Yeah, with the S client switch.
That's actually a great point, because not only can you use the S client switch, but you can have it dump out certificate details.
Another way to test from a different kind of client would be to use curl or wget, and there are command line options to tell it what trust scores to use.
We use Nmap a lot with the script SSL-cert, and that just immediately dumps out the cert that's used on that specific port at that specific IP or FQDN, and it'll tell you the expiration. That comes in really helpful for us.
And this is kind of new, but curl version 8 has some capabilities for dumping out certificates as well.
But those tools tend to be based upon whatever your underlying OpenSSL implementation is.
Yes, especially curl.
But with OpenSSL, you can actually create a CA certificate, an intermediary CA. There are various profile files that you can use when generating those certificates.
Right.
To tell it what attributes the certificate's supposed to have.
Yep. So if you're gonna set up a server, like I said, start with OpenSSL and create the certificates on the command line. That way, it's less of a mystery if you have a tool doing it later.
Right.
But that's really good point. I should talk about in the future. Talk about those tools.
I was going to say, have you seen the NAR-TAC IIS crypto GUI utility?
I have not.
I'll send you a link. It's just a visual representation of the registry settings on a Windows box, and it tells you if TLS 1.0 or SSL 3.0 is still enabled. And that's come in really handy for us when you're troubleshooting a connection to a secure system. You can kind of weaken it, and if it connects, then you'll know the client can negotiate at TLS 1.2 or something like that. So that comes in real handy. And then obviously the SSL cert website shows you the cert chain and how it got it. The SSL Labs.
Yeah, Qualys.
The Qualys, if you run the Qualys SSL Labs against a site, it'll not only test how secure it is, but if you dig into if you expand like the middle section, it'll tell you what physical parts of the keychain were provided from the server and which ones it inherited from its local cert chain. And that's come in handy because somebody sent the cert and the key, but not the intermediate. And you see in the Qualys report, I've got 1 and 2 and 4, but I don't have 3. And so it was a really nice visual way as people are learning to see what the cert chain looks like. And it's even more helpful when you screw up the cert chain order, because it'll tell you that you sent the key first and then the intermediate and then the cert, and that's out of order.
Yeah, I did actually have this in my speaker notes, but yeah, when you create that the certificate bundle with your intermediate cert, order matters.
Well, it's not supposed to, but it does in the actual implementations. But that's kind of what I was talking about when I talked about kind of two sides of the same coin. Is you want to focus on PKI and certificates and what they are and how they work, but how they work in the TLS protocol is kind of its own separate thing entirely that you can spend a lot of time on.
Yes.
That will just take you away from explaining and talking about the PKI parts. And then the third kind of leg to all this is the key management leg. And that's a piece that typically tends to get ignored or passed over or completely glossed over. And that's the piece that we're finding is increasingly important. More so than tracking your certificates. Like people think, oh, well, I'm issuing certificates, great. And then, but the real question is, okay, you're issuing all these certificates to essentially certify the identity of keys. Who has these keys? Who has access to them? How are they being controlled?
Yep.
How do you know if they've been compromised? Does the person who has one of these keys know what to do if their key has been compromised? And those sorts of questions. And those are all key management questions, but they're kind of outside of the scope of, we're just talking about PKI. But it's an integral part of it. And the other part is certificates that are not used by TLS. There are some very unique circumstances that are present in the use case for TLS that simply don't apply in other use cases. And in particular for client identity certificates, and more specifically in signing certificates, whether you're signing data or whether you're signing code. Because when you're signing things, that certificate represents an identity, and the identity doesn't expire. The identity typically is very long-lived. And so for that use case, which is not TLS, the use case specifically requires long-lived identities. Just like your signature on your driver's license doesn't change when you renew your driver's license, because your identity didn't change, just the license for you to do something changed. And certificates are very much the same kind of concept. And the only reason that we are able to replace certificates for TLS as often as we do is because the validation of that identity and the length of existence of that identity is only for the duration of the session connection with that server.
Yeah, that's getting a little bit deeper than I wanted to get, but
that has to do with TLS, and that has to do with the use cases for the specific kinds of certificates you're issuing, not necessarily PKI. So that's why I said there's more in-depth nuances there, but you do have to be careful that not everything is TLS, and all of the things you do for TLS to work are not necessarily true for all of the other places that you use certificates.
Yeah, and I guess one thing that I was wondering is how many people do you guys use client certificates much?
Well, I do. We do, because we use APIs. And as far as mutual TLS is concerned, in what we call the attended use case, where there's a person and that they're interacting with a system, a client identity is typically not part of that. That's part of the whole reason all the public CAs are withdrawing from issuing client certificates, which is going to happen next May.
Oh, I didn't know that.
Yeah, they've all pulled the plug on. They said nobody's using client certificate. It's too much of a support headache, and so Google decided they are pulling client certificate support from Chrome. And so, because the only place that the client identity should be automated is really to establish the identity of the client to the server in an automated way. Because in a browser, it's a user and you're talking with the user. And so the server can simply ask the user, give me your username and your password and I'll log you in. So the server interactively queries and obtains the user's identity. And in that context, the network identity, which is what the client certificate would represent, is the network identity of the client, isn't really relevant to who's using the network, if that makes sense. And then the other part is it breaks all of the inspection protocols.
Oh, right. Yeah. Break and inspect becomes
critical. Yeah. So you're not really connecting. You don't have a direct unbroken connection between the user and the server anymore in today's modern contexts. And so Google, and I think rightfully so, felt that the value of supporting that outweighed the technical underpinnings of implementing that support. And so they pulled it. And as a result, they said, as of next May, it will be gone from Chrome, and we will no longer be issuing client certificates. And so since the browsers would no longer be supporting any use of client certificates, all the public CAs pulled their support, and they said, we're just not going to issue certificates for both client and server. We're just going to issue server certificates only.
Oh.
And historically, the reason they did issue client and server certificates both was because they didn't know how you were actually going to be using the certificate. And so in order to avoid the support burden of having to explain to users, oh, you're using this certificate as a client certificate, you needed to ask for a client certificate, or you needed to ask for both, or you asked for a client certificate, but you really wanted a server certificate. And so they just said, we're not going to entertain any of those support obligations at all. If you want a certificate, we're just going to issue it and you can do whatever you want with it. And so, we're not the ones to blame for giving you the wrong kind of certificate for what you wanted to do with it. So that's how they simplified things. That's why they're all client and server. And with Google pulling browser support for clients, there's no clients that support client certificates to be presented to the servers. And so the only use case where that's useful is what we're finding is really in edge communications between my organization and your organization, where if you are accessing my service, I want to give you a client certificate that you have to use to authenticate to my service so that I know who you are before I let you in.
Yeah, there's a lot of
that's kind of the use case that we're finding, but that's really the client certificate is really embedded at the edge of the network. So it's your egress network endpoint is talking to my network ingress endpoint. And that's my server certificate. And so your client certificate represents your network egress endpoint, which is where I see your clients come from. But this only provides a secure connection between your edge and my edge. It doesn't provide any protection or confidentiality or integrity controls on the data from the sending client to the service provider inside of my ingress.
Right. My best practice there is for the ingress server to generate a token to go with the data. So it kind of and since that token can be signed, it came from the ingress server. It's not end-to-end.
Well, that's using OAuth, and that's typically what's done as an alternative to identifying, authenticating, and authorizing the client identity.
Well, no, I'm saying the client goes to the ingress server. The ingress server gets the client certificate, so it has strong authentication of the client, and then it takes that strong authentication of the client and repackages it in a signed token to send along with the data, so that the ultimate recipients, the services that ultimately receive that, have basically a token that vouches for the identity of the client.
So you're using the client certificate to generate an OAuth token, and that's returned on the request.
Yeah, well, actually,
Straightforward.
Yeah,
That's pretty straightforward.
Yeah, so yeah, but basically the machine-to-machine stuff is
It's a machine-to-machine context. That's where really the only point where we found it's useful. But even then, because TLS is no longer an unbroken sender to receiver secure channel, it's only network endpoint to network endpoint. And the network endpoints almost always are never the sender and the receiver.
right, but
So you're not securing the whole connection.
right, but your point about authenticating the sender endpoint, that's a zero trust architecture,
Right, but the network endpoint is not the sender.
right, and you can
I'm
actually
talking to your firewall.
But
I'm not talking to your client PC or your desktop behind your firewall.
But the thing is if the client endpoint doesn't have that certificate, then it's not a legitimate client endpoint. It's not. So you're not talking to somebody who stole the client credentials, unless they also stole the client certificate.
Well, but that has to do with your authentication requirements for your service endpoint.
Yes.
Which as a client, you have no control over.
As a client, you do not have any control over. So this is, obviously imposed from the server side, but and then the DoD has a huge, the U.S. government has a huge installed base of PIV cards. So,
right, but that would be something where the application is performing that authentication using the PIV card.
No, that's
the operating system in the browser.
And so they're using the PIV as the client certificate.
There is a certificate stored within the PIV. It is a card. The PIV card or CAT card holds the cert.
Holds the TLS certificate.
Yep.
And not just a data signing certificate.
Right.
That's correct. I mean, it has one.
Well, it probably has a whole bunch of different certificates.
Yeah.
Hey, Charles.
Yeah.
I just wanted to say, if you look in the chat, I put a link to the IIS crypto. It's just a Windows GUI that you can download and open. It'll show you it's a visual representation of the registry switches of what is enabled on that server. Is TLS 1.0 enabled, etc. And you can turn it on and off and reboot. You can templates, that stuff.
Yeah, I got that.
Yeah.
Thanks for that.
The second one is Uptime Kuma that we've discovered. Some people will use it because it has a certificate expiration checkbox. So you can have it check some of your internal applications. And if the cert is going to expire in 30 days, that app can tell you, so that you don't have to create calendar reminders or monitor it some other way. It just checks all of these URLs. And when the cert's coming up, it'll tell you, as opposed to one just expiring out from under you.
Yeah, I should really be keeping track of that, but that's a really handy feature though.
Yeah.
All right. Well, we're at the end of our time box, and I've got to finish up some other stuff. So, thank you everybody for attending, and thanks for the discussion and the tips on improving the.
Yeah, it was a very good overview, and one of the things that I wanted to note about when you were talking about the order of the certificates that are presented by the server to the client. The reason that you have to present all of the certificates in the chain from the end entity or the server certificate all the way up to whatever root signed it is because the server, when you receive a connection from an anonymous unknown client, you don't know what certificates are trusted by the client. And so because you don't have any guarantee or knowledge of what certificates the client has or does not have, you don't really have a choice but to send all of them.
Well,
So
yeah,
that's why you
really
send all of the
shouldn't be putting
certificates to the client.
really shouldn't be putting intermediate certs in your trust store, but some people do. So
Yeah, some people do because they're using intermediates, for example, to disambiguate between different environments. And when you trust a root, you are trusting all of the certificates issued by that root.
right.
And you may not necessarily want to do that. You may only
Well,
want to trust the
in that
certificates
case, you
issued by
want
an intermediate.
In that case, you want a different route, because if you have different use cases, if you have different policies for issuing certificates, that goes down to the root, and you shouldn't be
Not
using.
necessarily. No, it's the issuing CA. So you could have a CA that issues certificates to devices, and a different intermediary that issues certificates to users, and a
Right.
different intermediary that issues certificates for infrastructure services.
And
But they all chain up to the same root, but they're different intermediaries. And so the trust stores would want to anchor their trust to specific intermediaries.
No, I disagree. I think you want to anchor your trust to the root, and you can use that the issuer information to make some determinations, but ultimately it's that root certificate is the anchor.
But that's all client policy. And as the client policy, the server has no knowledge and can make no assumptions of what that is. So that's why as a server, you really should be sending all of your certificates from end entity up to the root. Well, except for the root.
Except for the root.
Because the client either has the root or it doesn't. And if it doesn't, then none of it matters anyway. So you don't need to send your root to the client, but you do need to send the end entity and all, or the leaf node and all intermediaries up to before the root.
Yep.
Because you don't know what the client has or doesn't have.
Yes, definitely. But they should have your root CA if they're going to trust your certs. So
right, if they don't have your root, then it doesn't matter anyway. So you don't need to send your root to the client.
Right.
Because they would be validating your intermediary cert that you sent up to the root that is in their trust store.
Yeah, good. That was I really appreciate your insights on that. But I got to drop off and
yep.
So
excellent. There's no end to the depth in which you can kind of get into the details, and sometimes it matters.
Right. All right.
Thank you, everyone.
Good night.
Thank you, Charles. Have a great evening.